I'm Andrew Thompson. I am the VP of Engineering at Nova Labs, which is formerly known as Helium. We renamed ourselves like last month. But I'm also sort of known for the author of GenSMTP, everybody's favorite email library, and also the logger that is not spelled like the beer, not like the new logger in OTP, but I wrote the old one that they replaced. So I've been around, the Erlang ecosystem for a while. So today, I want to talk to you about, Erlang's very famous for distributed systems, right? I mean, it's used for all kinds of research in distributed systems. Lots of distributed systems are implemented in Erlang. But they're usually what I would call trusted distributed systems, where the system, you run all the instances of the node yourself, for example. And so we're going to talk about what happens if you want to do distributed systems when you don't trust everybody involved. And the mouse is going to do the thing. We're going to have to go through this a few times. There we go. OK, so this is probably my favorite quote about distributed systems, because it really captures distributed systems are really about failure, right? And the way in which they fail and how they handle that failure can really influence how they operate in the field. And obviously, the very pithy observation here is that, a distributed system is when something you don't realize breaks, it breaks you too. And again, I want to talk about what can we do in the face of those kind of failures. So, there's really, I would say, in my opinion at least, three kinds of distributed systems. So, trusted substrate is the one that you're probably most familiar with. We've got Raft and Paxos and distributed Postgres and all these kind of things. And then we've got sort of untrusted, where the nodes run on sort of arbitrary hardware in arbitrary places on arbitrary networks, but the nodes have some kind of identity attached to them. So you know roughly who they are. And in that class, we have things like BFT and Nakamoto consensus. And then finally, there's a class that exists. There's research about this, which are sort of like truly untrusted systems. As I said, there is research there. I don't have a lot of experience there, and that stuff is still, I think, really not something you'd really want to deploy. But I think the other really common instance of that is people write this last kind of distributed system a lot by accident, and they learn what happens when these systems have all kinds of bad failure modes, but they find them out in the field. So we're going to talk about the second class here. So Erlang is all about trusted substrate consensus, right? Distributed Erlang itself, if you get into an Erlang cluster, you can do anything on any node, including call into the operating system, whatever you want. It's essentially remote root, right? So you do not want to allow arbitrary nodes to join your distributed Erlang cluster. Amnesia is the same, right? Amnesia assumes that all of the nodes in the Amnesia cluster are roughly working correctly. Global name registries, gproc, PG, all those kind of things. Again, they operate largely in the idea that the other nodes are trying to do the right thing. And then, the really big thing here is that in Erlang, you can basically put any message in any other process's mailbox at any time, and that process has no idea how that message got there, right? So you can trick the system in all kinds of ways by putting the right message in the right mailbox at the right time, and there's no authentication or access control there. So when the internet first started, right, it was the ARPANET, and a bunch of universities got together and connected their campuses together, and they had these sort of very naive protocols where they said, okay, well, we're all universities, we're all cool. We're not gonna try to, defeat each other or anything like that. So you have a lot of these very old HTTP is kind of more modern, but I'm just lumping it in here anyway. But a lot of these very old internet protocols, right, they basically assumed good faith on the part of everybody participating, right? And unfortunately, we've learned that this is actually a terrible idea on the internet. So if you look at these protocols now, either they no longer exist, or they've gotten a whole bunch of sort of layers put on top of them to defeat sort of attacks against them. So SMTP now has the sender policy framework and DKIM and RBLs and all kinds of stuff to control people sending emails, too many emails or spamming or anything like that. BGP is a similar thing. Or originally, anybody could claim a route for anything, basically. And so, you still see that happen sometimes when an ISP forgets to filter a BGP prefix, and then all of a sudden all the Twitter traffic goes through China or something like that, right? Like that protocol is still fundamentally a trusted protocol, except that we have this layer on top that filters who we trust. And then, DNS, a similar approach. We've got DNSSEC, we've got DNS over HTTP. That's ongoing fixing that as well, because DNS hijacking can be a big deal. Telnet's basically dead, thankfully. We replaced it with SSH. We learned some good lessons there. And HTTP largely has been replaced by HTTPS, which is not always needed, but it's probably for the best. So, we learned that you shouldn't deploy naive software on the open internet, right? You don't know who else is out there who's connecting to your software and sending it messages and stuff like that. So, there's a few solutions to this problem, right? And so the first one is we say, okay, well, we can't trust anybody, but we can trust specific people. We can say, okay, we think that this organization or this company is broadly trustworthy, whether it's Google or it's Facebook or it's Apple or whoever, and we say, they're okay. We like them. Another approach you can take is you try to remove the need for giving trust to other parties, right? You can say, well, what can I do if I don't trust anybody? Or really the last option is you just say, well, the internet was a mistake. Let's forget about it, and let's get rid of let's not hook computers together anymore. It's not worth it. And so obviously we chose option one, right? It was the easy choice, and we saw a huge consolidation in a lot of services in the late 90s, early 2000s, and sort of going on to today. So, nowadays there's really like 5 email providers. Realistically, it's actually very difficult to run your own. I sort of do one, and Google just likes to block me constantly because I'm not doing the latest and greatest thing or whatever. So, there is certainly a lot of consolidation there. We've seen a lot of forums and bulletin boards and stuff like that move to Facebook. Basically every video game community is now on Twitch or Discord. Most people don't run their own website anymore. Back in the 90s, everybody would deploy HTTPD and have their own little static site or a Perl CGI site, something like that. But most people don't do that anymore. They either, they have a site on Facebook, or they have a GitHub pages, or they have something else where it's hosted by somebody else because they don't want to deal with the headaches. And then, the other thing that's really appealing here is we put a lot of research into how do you make, how do you do trusted consensus, distributed trusted consensus systems. So we're taking a system and we're sharding it horizontally, but we do it in one data set or on a private network that we control, right? There's been a ton of research in there, Raft, Paxos, all the flavors of that. We've got distributed Postgres, we've got all those, we've got Erlang, right? All that research and all that money has been dumped into solving these kinds of problems. So, we solved that problem, right? We don't have the issue of, we've solved the trust problem, right? Well, there's a few problems here, and I think we've really seen those come up in the last 5 to 10 years, right? Like, we put all our eggs in one basket in a lot of cases. So when US East on AWS goes down, everybody knows about it because a lot of stuff ends up running on US East, right? or people rely on a program or a service, and that service it goes on an incredible journey, right? Google Reader's a good example. Yahoo Pipes is another one. What happens when the service you depend on is no longer the provider is no longer commercially interested in providing it, right? That's a big question for a lot of people now. Like, I think Google Reader was a really transformative experience in that regard. What happens when you decide that you're in a bad relationship with a company? Like, for example, a lot of people will tell me, "Oh, I'm on Facebook, but the only reason I'm there is because all of my friends are there. I don't want to be there, but I have to be there." And I'm not on Facebook, but I can certainly see why people would have sort of a conflict there. And then, right, like, if your service is owned by somebody else and they decide how the service is going to change, you're stuck with it, right? Your favorite video game, has an update, and now whatever your character is built in some specific way doesn't work anymore, right? They changed some, I don't know, they changed some area of effect field, and now you're whatever. So, people, you don't have a choice. You just got to go along with it. And then, another case is, what happens when that company or that service decides they don't want you anymore, right? I mean, YouTube DL was DMCA takedown. It was illegitimate, it turns out, but they got taken down, right? It came back up again, but as another sort of, you can see why, these are all sort of things that trigger people to reevaluate their relationships with centralized services. So, my opinion in this is that if you have a centralized service, that centralized service embodies the decision-making around that service. Like, you as a user are in a fundamentally different role than the person providing that service. And, as much as you may hear about community engagement or, whatever, you are essentially, at the end of the day, not the party with the power in that relationship. And so, what else can we do? Do we go back to the 1970s and say, the whole thing was a mistake? Well, while we were doing all of the things that we've been doing for the last 20, 30 years, there were some really interesting sort of papers and research happening sort of in a backwater, right? So the original paper on this was talking about reaching agreement in the presence of faults in 1980. A couple years later, they actually named the problem, right? And so somebody decided we're going to call it, well, originally it was going to be the Albanian generals, but people realized that people in Albania might get upset, so they decided to name the problem after an empire that's been defunct for 1,000 years. So the Byzantine generals problem paper really frames the sort of the challenge you have in these untrusted consensus systems. And then quite a long time later, there was actually a protocol implemented or designed that could actually work around the problem. So as you can see, it actually took quite a long time. There was almost a 20, quite a long gap between the statement of the problem and really the first viable solution to it. So, you hear the term, certainly in this area of research, you hear the term Byzantine general a lot. And so what is a Byzantine general? And in general, a Byzantine failure is the most general case of failure where anything can go wrong, like absolutely anything. If you've ever heard of undefined behavior in C, where if you do something that's outside of the C standard, the compiler is free to do anything, including having demons come out of your nose. It's a similar approach, right? Essentially, a Byzantine failure node is allowed to do absolutely anything that it wants. And so, the original sort of problem statement was, there's a city we want to attack, and I have some generals that are all in charge of armies, and they all have to attack the city at the same time, or the attack fails. But the problem is some of my generals, I don't trust them, or I think that some of them are traitorous, and they're not going to do what they say they're going to do. And the solution, the protocol is coming up to a solution for that problem, where basically everybody either attacks or nobody attacks, so you will either not attack or you will win the battle, right? And that's the problem statement in the simplest terms, to talk about what a Byzantine general is. And it's one of those generals in that model. But essentially, it means that you can model that as there's just nodes in a system. Those nodes can do anything at any time. And I want to make sure that they all do the thing, or none of them do the thing. So it turns out, in the research in those papers I mentioned, there's a formula you're going to see, and it's 3f plus 1. And what 3f plus 1 means is that f is the number of Byzantine nodes you can tolerate and still sort of maintain the integrity of the system. So, it means that just under a third of your nodes can be completely have arbitrary behavior, whether it's malicious or whether it's just accidental. They can be turned off, anything. And as long as that number is less than a third, less than a third, you can actually make progress, right? And and when you exceed that threshold, your system can make a choice about how it wants to proceed. You can say, okay, well, we're just going to go. If things happen, we're just going to continue, or we're going to say we don't have enough agreement, and the system is going to come to a halt, and somebody's got to come in and see what's wrong with it and fix it, right? So you have choices in what happens when when that threshold gets exceeded. So, why is BFT? BFT was really obscure for a very long time. You may have heard of it now, but for a long time, it was really a very obscure thing. Because part of it was, in the late 90s, we were all busy building the Facebooks and the MySpaces, and we were solving the problem with centralization because that was easier and more performant and stuff like that. Practical BFT also, it doesn't work well on asynchronous networks. So James Mickens has a great slide where he shows the messaging complexity of PBFT under arbitrary timeouts. And basically, the number of messages the system starts spewing to try to agree on what's happening, it grows exponentially. So that's no good. You have to be very careful with your timeouts with PBFT on the internet. And because the internet is going to do what it's going to do, it's essentially impossible to tune those perfectly. PBFT performance also wasn't great. And then finally, PBFT doesn't defend against a Sybil attack. And so what's a Sybil attack? So a Sybil attack is where you essentially have a reputation or identity system where you can create arbitrary numbers of identities that you control. And so anytime the system wants to have a vote on like what does the majority of the system want to do, you can just overwhelm that vote with your army of sock puppets, right? And so the ways to defend against a Sybil attack are either you have some central authority that adds nodes, so that, essentially says this is a real node, I'm going to add him to the list of trusted identities, or you tie your identity to a verifiably scarce resource. And that can be a lot of different things. You could do an IP address if you were feeling spicy, or it could be a government ID, it could be, anything you can think of that's essentially you can't make infinite copies of, right? And so the big fish in the pond here was Bitcoin came out in 2009. And I think that really, again, BFT had been sort of there, but nobody was really doing anything with it. For example, I think one of the big use cases of it was Boeing used it in airplanes to build a consensus system around sensors. So if you had conflicting inputs on the plane, you could use a BFT system to say, okay, well, the majority of the system agrees that the plane is not crashing, so we're not going to, take some action that the plane is crashing. Maybe one sensor is bad or one computer is bad. And so that's sort of one of the big uses of it up until this point. And so what Bitcoin kind of did is it showed that there's a use, however controversial it might be, for a untrusted distributed system, right? And they also basically the way that Bitcoin was revolutionary is that it coupled its proof of work system. It used the proof of work system to basically solve both the Byzantine generals problem and the in the Sybil attack at the same time. So essentially, in Bitcoin, you have one CPU, one vote, and also the fastest node to find the next block wins, roughly. And so that has really kickstarted the research into untrusted consensus systems again, right? We've seen dozens and dozens of new papers in this field, right? So Tendermint is a big one. It was used, I think, from some of the IBM blockchain stuff. Hot stuff comes out of VMware, I believe. And my personal favorite is called HoneyBadgerBFT. And so HoneyBadgerBFT came out in 2016. And it is the first of a whole new family of BFT protocols. Most other BFT protocols are in the PBFT family. HoneyBadger actually does things very differently. It is still a BFT protocol, but it is very differently shaped than what you would expect if you're familiar with PBFT. So its big takeaways, its big changes are that it says that we're going to embrace the asynchronous state of the internet, and we're also going to be censorship resistant. So being censorship resistant means that essentially it's difficult for any member of the system to block messages it doesn't want to show up in the system. And that can be really important. If the system is trying to update some state and the nodes that are making the updates to the system don't necessarily want to change that particular piece of state, if you're not censorship resistant, they can deny that information essentially infinitely. So censorship resistance means that it weakens the power of the nodes in the system to resist changes to the system that are legitimate, that they are potentially not interested in doing. So it's a little bit convoluted how this actually works, but essentially, every member in the system encrypts a proposal to how it wants to change the system, right? How the state machine needs to advance. And that's then broadcast to all the other members over what's called a reliable broadcast protocol. And at that point, the group then says, okay, which proposals have I seen? And it runs a very complicated protocol called the Byzantine Binary Agreement Protocol, which does all this work to agree on one bit. It says 0 or 1, true or false. Basically, did I see that proposal? And then did enough of the nodes see the proposal, right? So essentially, we're agreeing on which proposals we saw. And once 2f plus 1 of those proposals have been completed and the BBA has been resolved, all the remaining BBAs get false inserted into them. And these are guaranteed to terminate. So essentially, the system will converge. There's a whole bunch of coin flipping and voting and revoting and stuff that goes on in BBA to basically guarantee that the protocol will terminate. And then once all of the BBAs have terminated, we now know of all the proposals that were proposed, which ones we've all agreed on. And then at that point, we do what's called a threshold decryption, which means that all of the nodes have to work together to decrypt the message. And then at that point, they've already committed to what was proposed. And they can no longer rip out messages that they don't want. They've already said, I saw that proposal. I didn't know it was in the proposal, but I accepted it, and now I have to live with it. And that's how censorship resistance is actually provided, right? Yeah, and so as I said, right, it means that nodes cannot censor information that they don't want to see. So to make this work, we need something called threshold decryption. And threshold decryption relies on something called the distributed key generator. And the distributed key generator is probably my favorite thing I didn't know about in computer science before I learned about this thing. It's super cool. But essentially what it is it's a way for a group of nodes to generate shares of a key, of a private key, such that no single node knows what the private key is. Which means that you can do all kinds of neat stuff without having to trust anybody else in the group, right? You can essentially build arbitrary groups that can set up threshold threshold keys, which is, I think, it's just super cool. I'll get into how it works in a minute. And then, obviously, to decrypt a message or to sign a message, the nodes have to work together up to some threshold, and then they have enough shares of the private key that can be used to construct a signature or to recover the private or the plain text message. So there's an implementation of HoneyBadger out there now. So this is what I wrote, or we wrote at Helium. It uses Erlang DKG for decentralized key generation. It uses also uses a library called Relcast, which I'll talk about in a minute. But essentially, Relcast provides, under sort of the worst possible conditions, it will give you reliable message transport between nodes. And we've actually run HoneyBadgerBFT at 50+ nodes over the internet on varying hardware, and it does actually work, right? This is actually for a BFT cluster. This is actually a pretty big number. So it does scale, which is pretty cool. So the DKG we implemented is based on a paper called Distributed Key Generation in the Wild from 2012, and it was the first practical asynchronous distributed key generator. Before that, we had a bunch that either required a trusted dealer or they required synchronous networks, which essentially don't exist in the real world. And this was the first one that really solved the asynchronous problem. And so essentially what happens is you generate homomorphic shares of pairing-based cryptography keys. And so homomorphic shares mean that you can actually combine the shares together to create another key and stuff like that. And then pairing-based is a new kind of cryptography that's sort of coming out to the fore now. You may have heard of it. It's sort of, it's come out after elliptic curve. So it's sort of, in a way, it might be the next sort of elliptic curve in the shift of sort of cryptography. It's essentially, it operates over the principle of you map a value in one finite field to a field to another finite field, and that mapping, there's complexity around. There's basically, without knowing that mapping, you can't. Well, anyway, it's probably too complicated to go into here, but it's a really interesting new way of doing cryptography. And then, crucially, the threshold of the key that you generate, how many nodes need to collaborate, can be configured. Usually, you set it to the same as your Byzantine fault-tolerant threshold, but in the library, you could actually set it to something else if you wanted to. So, and here you go. There's an implementation of that as well. Originally, we implemented it over some fairly old and crappy curves, the SS512 curve and the MNT224 curve, which are basically considered pretty useless at this point. But that's what we could get work at the time. Last year, we upgraded it to work over BLS 12-381, which is kind of the new hotness in pairing-based cryptography. That's the sort of darling key at the moment, curve at the moment. And it also uses Relcast for reliable transport. It turns out both HoneyBadger and the DKG require sort of messaging guarantees so I wrote this common library to provide it for both of them. So how does the DKG work? So a leader is selected. And I'm going to gloss over this because we currently just pick the first node in the group and we say, you're the leader. We don't actually do a leader election. You can do a leader election. And the protocol says you should. For our purposes, we don't need it. But you could implement a real leader election, but we didn't need it. So, and then each member generates a polynomial, and it gives shares of that polynomial to all of its peers, and it doesn't reveal the constant value of the polynomial. And we have this similar approach where a bunch of nodes, once we have enough proposals, the leader then says, okay, we're going to make the key out of this set of proposals. And then basically every node can combine all of the shares from all of the proposals that were accepted. Those are combined to form new shares of a new polynomial that nobody knows the value of because no single node knows what all those constant terms are. And that's where the key shares come from. Essentially, there's some fancy Lagrangian interpolation and all sort of secret sharing stuff that goes on, but that's roughly how It's roughly how a distributed key generator works. And so the important thing at the end is you have a bunch of nodes, and they all have shares of a private key. You know what the public key is, but nobody knows what the private key is. So anything that's done with that key has to be done collaboratively, which is a really powerful primitive for untrusted distributed systems. OK, and so another library we have is called Relcast. And what Relcast does is essentially it provides durability for these protocols. So these protocols both have both broadcast and unicast messages. So essentially, either I'm going to send a message to all the nodes, or I'm going to send a message to one node. And so the protocols can return messages can return to Relcast and say, here's messages for this particular node, or here's a broadcast message. Every single message is stored in RocksDB, durably in RocksDB, on the sender side until the client acknowledges it. The client takes explicit responsibility for it, and then at that point, it can be deleted locally. And the client, once it gets a message, it will write it locally before trying to process it. So essentially, it writes it durably, sends the ACK, and then tries to process the message. And in addition to all these messages, the protocol state is stored in RocksDB. So every single time the state of the protocol changes, that's also durably written to RocksDB in the same, in the same vein, essentially. So what happens is that essentially you can crash this process at any point, and assuming there's no disk failure, assuming that the committed write has made it to the disk, the protocol will continue. And I've seen it where, the node would come up for 5 seconds, crash, come up for 5 seconds, crash, come up, and it would still make progress. So it's actually a really powerful primitive to be able to have, right? So and you could do this for a gen server, for example. It's just any kind of messaging between processes that you want to have be reliable, you can use Relcast for. It's not just for this stuff. It's a general approach to something. So you can implement a gen server over Relcast where every message that came in or out of the gen server would be durably preserved. And so, OK, we've got a bunch of fancy protocols and storage and message storage stuff, but how do all these things talk to each other? And so we also implemented Erlang libp2p, which is, unfortunately, it's not a compliant implementation of Protocol Labs' spec right now. We started so early on this, they hadn't actually implemented a bunch of stuff in their spec, and so, or finished the spec, and so we kind of did some of their stuff, and they took a different direction, and we took a different direction. I would like to get it back to being compliant at some point, but right now, it isn't. We did some work to do it, but it didn't end up landing yet. But unfortunately, it's a lot of work to fix it at this point. So, but it provides a lot of nice things. You can gossip out events to other nodes, and it's a flood gossip right now because Byzantine fault-tolerant gossip is sort of an unsolved problem, although an interesting paper came out, I think, a couple weeks ago. But currently, it's a pretty unsolved problem, I guess. It also provides for peer discovery. So if I know I want to talk to somebody else, I can ask, does anybody know where that is? Does anybody know where a particular host is? And they'll give me information about it. Essentially what's called a peer book, and a peer book entry is like a phone book entry. Here's who I am, and here's where I can be reached. It provides for connecting to arbitrary or random peers. For the most part, you only need to connect to random peers. You just want to be a part of the network. But sometimes, like if you're doing, running in the HoneyBadger group or doing a DKG, you need to connect to particular peers. And it provides for both. You can negotiate the protocol that you want to talk to another peer with, and you can also negotiate the version of that protocol. And you can say, I really want version 2, but I will also do version 1 if you support it, and it will sort of converge on the highest shared version of that protocol. And it currently provides for Relcast. Relcast shouldn't live in libp2p, but it does for historical reasons, but it does do it. And it also provides a secure channel over which to do it. Essentially, the message is encrypted and authenticated, again, because these protocols are not tolerant for the messages exchanged being public or injections into that stream of messages. So That's why they have to be a secure channel. It also deals with NATs and all kinds of terrible internet conditions. If a node is behind some really difficult NAT or double NAT or triple NAT, it will essentially try to connect to somebody with good connectivity and then ask that peer to provide it a relay address so other peers can connect to it if they wish. So even if you're behind a NAT or a firewall, there's a good chance that you can actually still participate in the network. And it currently is holding together, barely, over 800,000 nodes globally, which is kind of remarkable. All over the world, over the worst internet connections you've ever seen, but it actually does mostly do the thing, which is pretty impressive. So what I really wanted to show you today with this talk is that there's a whole toolkit here for building systems of this class, right? Where you don't want to have centralized trust or trusted substrate deployments. You can actually build useful applications and useful systems. And there's a whole bunch of essentially state-of-the-art libraries out there on the beam to do this stuff in, right? And another really important thing is if you look at a lot of these distributed system libraries is that they conflate the application with the network, with the protocol, and you get this kind of ball of mud that you can't necessarily adapt to your own use case. Our libraries, we tried very hard to make them generally applicable. So they do not require any particular transport. They do not require any particular storage. They do not require. They know as little about the application that they're being used for as possible. So they are very general, and you could reuse them for lots of other things. There's also a bunch of other NIFs we've written. We've got stuff for, we needed a better erasure coding NIF. The one that was out there would segfault a lot, so there's a better erasure coding NIF. We've got a BLS 12 381 NIF. We've got a bunch of stuff for coding gain if you're doing weird radio stuff or unreliable transport stuff. We built a binding for Uber's H3 geospatial coordinate system. There's a whole bunch of stuff that we had to build to pull all this stuff together. And so it's all out there and it's all open source. Oh no. Oh, there we go. Okay, so one of the call to action in this talk is, first of all, I wanted everybody to know that you can build systems like this, and they can actually do useful work. But we don't get a lot of open source contributions for these libraries. I think a lot of people don't know they exist. But we could use help. You know, if this is interesting to you, I would love to have PRs for documentation, better tests, you know, any of this stuff. We built them and we deployed them, and they sort of don't get a lot of use because, you know, Erlang code, right? Erlang code, it just runs and you forget about it. And so these are sort of suffering from the Erlang code disease of, you know, the squeaky wheel gets all the grease, and these are not the squeaky wheels. Well, libp2p kind of is, but even that, it's not as squeaky as you would expect. And so we're also hiring. So if you are really interested in very sort of cutting edge distributed untrusted stuff, you know, let me know, or contact Nova, right? We are always looking for people to help us make this stuff work better. So thank you. And I have 7 minutes for questions. All right.
You have an eternity of question time. Do we have any questions in order? Butterfly. Do we have any questions in the audience? Yes.
Uh-oh.
Please talk into the mic as an ice cream.
You kind of just mentioned in passing leader election. Leader election is not an easy problem in a Byzantine network.
Nope.
So is there something similar for that, or does the HoneyBadgerBFT protocol include leader?
HoneyBadger is leaderless itself.
Yeah.
So it does not. There is no leader in HoneyBadger. The DKG does have a leader, and I intentionally did not essentially what I said is, if the first node is not going to fulfill its duties as a leader, we're just going to throw that whole election. We're going to throw that whole DKG again and try again later, right? It's cheap for us to discard it, but that certainly is a hard problem, and I could only tackle so many hard problems at once. But yeah, a Byzantine leader election would be really nice, but don't have it right now.
Yeah, thanks.
Yes, are there more questions in the audience? Otherwise, I have a question. Yes, please come forward to the ice cream cone, as it shall be forever be known as.
Well, you said you.
Håller den som en...
Okay.
Yes.
So you have several nodes that needs to participate to sign something.
Mm-hmm.
Could you say something about the trade-offs of latency? Because signing something is going to take a lot longer when you have to agree on the signing, I suppose.
Yes, these are not okay. So they're surprisingly high performance, or they can be, but certainly if a decentralized system is always going to be slower than a centralized system, right? Because you do have to have that agreement phase, or that it's a protocol round essentially, where everybody has to say, oh yeah, well we all agree on that, and we're gonna submit all of our signature shares, and all this stuff's gonna happen. So yes, you pay a cost, but with modern hardware and with some of the better pairing-based curves that are out there now, and better library implementations of those curves, it's actually not as terrible as you would expect. It's not free, but it is eminently doable in a reasonable amount of time.
Okay. Kenji, are you online? Are you here?
Hi.
Yes.
I've already posted my question on the Q&A section.
Yeah, could you please tell us? It's more interactive.
I was going to ask whether there's a problem called there's a spellworm called FLP impossibility, which says that if everything is asynchronous, a one node failure will kill whole distributed system, and no consensus would be successfully made. What this kind of problem? I'm not familiar with the distributed consensus at all, but
Yes.
Is there any way to overcome this kind of failure in your proposed system?
So obviously the FLP result is relevant here, but essentially what happens is, how do I want to put this? It's a complicated question, I guess. I don't have. Okay, I'm not prepared to answer that right now.
Okay.
I wish I was.
Actually, I have to tell you that I don't know what I'm really asking by myself either.
Okay.
So,
what I will tell you.
Okay.
Is that the system handles all kinds of failures, right? Obviously, it will handle up to F failed nodes of any kind of failure, which I've seen personally many times at this point. But also, one of the things, we're out of time. But yes, it does handle them. I don't remember exactly how this relates to the FLP. I know that there is a relationship. I'll be honest with you, it's slipping my mind at the moment. But I will try to find an answer for that and let you know. But it is. Okay. We do tolerate arbitrary node failures as long as they do not exceed the Byzantine fault tolerant threshold.
All right. Thank you very much.
Thank you.
Lovely.
Good to see you again.
And there are at least one more question in the chat, so Andrew will make sure to answer them after the talk. Give it up one more time. Thank you so much.